stations, all stations. This is Army Lacrosse Project Command. At my command mark, the time will be running at X minus 20 seconds. Mark, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire. Missile away. X plus 5. X plus 10. X plus 15. X plus 20. X plus 25. X plus 30. Impact.
This is Headquarters Building, White Sands Missile Range. Inside are the front offices of the Integrated Range Mission. Let's look in.
Welcome to White Sands Missile Range. You just saw a missile test. Making such tests possible is our day-to-day job. By our, I mean the several thousand Army, Navy, Air Force, Civil Service, and contractor people who make up the organization we call IRM, short for Integrated Range Mission. IRM is under the command of the Commanding General, White Sands Missile Range. It is IRM's task to provide the Army, the Navy, and the Air Force with the range support demanded for successful missile tests. What is meant by range support? How provided? This is our story, the story of IRM. Let's begin by taking an artist's look at the White Sands Integrated Range. This is an all dry land area over 100 miles long and 40 miles wide, located between mountain ranges in the broad Tularosa Basin of southern New Mexico. It is uniquely well suited for missile testing. Now let's take a tour of IRM's facilities.
The surrounding mountains serve as excellent observation platforms for the hundreds of optical missile trackers. A stable platform is a must if these sensitive instruments are to get the precise flight data vital for proving and improving modern missiles. Clear weather is also a critical factor for instruments which must photograph supersonic missiles at tremendous distances. The bright skies of New Mexico are most nearly ideal for this purpose. The broad flatland between the mountains makes possible the speedy placement of numerous mobile trackers at any spot necessary to meet the changing needs of the missile testers. And on this all-land range, components and instruments from impacted missiles may be recovered with minimum time and expense. On the other hand, missile recovery from overwater ranges is, when possible at all, costly and time-consuming. Moreover, on land, the impact point can be precisely located, an important factor in evaluating the performance of ballistic missiles. Recovering components and instruments is the daily job of hard-working range recovery crews. Recovered items are delivered to the White Sands labs for scientific and engineering study. At this missile test center for all three services, progress is made daily in missile development. Progress in range instrumentation must keep pace. In this building, some of over 100 scientists and technologists work for this purpose. They work to develop new missile flight data gathering systems. They work to develop new computing equipment for speedier and more effective reduction of missile data. And they work to improve presently used instrumentation systems. Let's watch some of that present instrumentation in action. This high-speed camera is being prepared to photograph the takeoff of a Navy tailless missile. An unmanned drone plane is the tailless intended prey. A specialized instrument tracks the drone. It is one of several like instruments which photograph intercept of the target by the missile. At widely separated range sites, other instrumentation crews prepare for the mission. The hundreds of instrumentation stations are so located that the flight of a missile fired from any launch site can be covered from takeoff to termination. Time is running on the tailless. Only minutes remain. All-weather electronic data gathering systems wait to follow the flight of the tailless. Taken all together, the various optical and electronic systems at White Sands comprise what probably is the best missile range instrumentation in the world. Now, in seconds, the tailless will flash skyward.
5, 4, 3, 2, 1.
Several of over 50 cine-theodolites record the supersonic missile's exact position in space. Far-seeing tracking telescopes record attitude and event data. For instance, missile spin rate, warhead dispersion, booster separation, or fin action. This is the Army's Sergeant, surface-to-surface guided missile. As the countdown nears the command to fire, scattered stations of the DOVAP Doppler data gathering system are set for the mission. From this tower, the Doppler signals are beamed to the missile.
5, 4, 3, 2, 1, 0.
Ground antennas receive the Doppler signals retransmitted from the missile. Inside the DOVAP recording stations, the signals are transcribed on film, paper graphs, and magnetic tape. The recorded DOVAP data, when reduced, will tell an accurate story of the missile's velocity, position, and range. Ballistic cameras are trained upon the missile to obtain highly precise position data. Telemetry stations are zeroed in. These stations receive and record as many as 28 channels of information from missile-borne instruments. Information radioed from the missile varies widely in nature. Commonly, data on such functions as skin temperatures, rate of fuel flow, and pressures are telemetered. A signal corps range-wide chain radar system also keeps an invisible electronic finger on the missile. One of the 5 chain stations controls the tracking of all stations. As the missile rockets through space, control passes instantly to the nearest chain station. Radar-controlled plotting boards trace the path of flight. Should the tracing pens indicate the missile will leave the range, this man will throw the switch to halt its flight by remote control. Not only what happens in flight, but exactly when it happens must be known. For this purpose, IRM operates complex timing generators. The generators feed any desired timing code over the Signal Corps Giant Communications and Data Transmission Complex to far-flung instrumentation stations. Tracking instruments record the timing signals on the same record with the missile data. Timing signals click the shutters on data cameras to ensure perfect synchronization in time of photographs taken from widely separated points. Range communications and data systems serve many purposes besides transmitting timing signals. Nearly 40,000 circuit miles of wire and cable, over 200 radio channels, and an extensive microwave system handle the enormous amount of communicating required to support missile tests. Missile test operations also require extensive air support, an Air Force contribution to IRM. For example, the Air Force flies a variety of drone target planes for missile tests, provides weather forecasting services, and operates a downrange airfield. Here is based an Army aviation unit, which spots where the missiles impact so that they may be recovered. The aviation unit also transports personnel and does many other jobs. To this building are brought the data from missile tests on the northern half of the range. Data gathered downrange are reduced here. IRM's modern data reduction facilities are extensive. From the photographic labs, where millions of feet of data film are processed each year, to giant scientific computers, which with incredible speed produce the final data needed by the missile scientists and engineers.
Very briefly, you've seen the basic tools it takes to get the performance data imperative for continued progress in the missile field. These were the tools, but how about the use of these tools? How managed? How coordinated? To get these answers, let's go to one of IRM's range control stations.
This man is chairman of the Range Scheduling Committee. Each day, he takes part in a telephone conference. Purpose? To schedule tomorrow's operations. At distant points, a representative of each of the three services is on the line. Technical advisors for major support functions, such as optical instrumentation, telemetry, DOVAP, radar, all listen in. Today's decisions rest on months of careful planning and preparation by both range support and missile test agencies of all three services. Many factors make scheduling tough. For instance, several tests are often conducted concurrently on different parts of the range. Other tests tie up the whole range. But in spite of difficulties, all work in harmony for the most efficient and economical use of test facilities. Even before the conference ends, the next day's schedule is going out over the wires to each of the three services. Duplicates are speedily routed to the hundreds of people responsible for support of tomorrow's test. The next morning finds the test schedule posted on perhaps 100 boards. This man is a range controller. His is the crucial task of coordinating the tests scheduled for today. In a few minutes, his job will begin with the countdown for a Nike Hercules, the Army's powerful package of supersonic destruction. Next in line, Army Hawks, a covey of deadly birds eager for low-flying prey. A land-based Talus, waiting its moment of devastation far above the earth. An Air Force Matador, set for a journey to end in a terrific termination. An Army Honest John, the rocket which revolutionized field artillery. An Army Little John, fast, small, but capable carrier of a big blast. An Army Lacrosse, light portable deliverer of prodigious power. An Army Nike Ajax, proved instrument of instant aerial destruction. An Army Corporal, America's first operational surface-to-surface guided missile. An Army Sergeant, designed to destroy far-distant land targets. And a Navy Aerobee High, sensitive probe for secrets of the high heavens.
All stations, all stations. This is Nike Hercules Project Command. We are firing round number NH-X03. Test directive number 608. Launching pad number 4. Type of target, QF-80 drone. Drone altitude will be...
Also in the range control room are coordinators for the various range support services. Over a number of communications nets, the coordinators instruct the men at hundreds of field stations.
All stations. This is instrumentation control. Time is running on Nike Hercules, X-minus 60 minutes. Instrumentation controller calling Terra 3.
Terra 3, go ahead.
Train your instrument on the launch site and track missile to intercept. Then track falling debris.
This is Nike Hercules Project Command. Time is running. At my mark, time will be X-minus 30 minutes. Mark.
Uprange at Holloman Air Force Base, the drone target plane will soon leave the runway. She will be guided downrange by a mother plane.
This is Drone Squadron Officer. Drone Squadron calling range control.
This is range control. Go ahead, drone.
Drone is airborne at X-minus 20 minutes. Drone calling range control. Drone is at altitude. Is range clear for entry into flight pattern? Over.
This is range control. The range is clear. Bring her into pattern.
Director aircraft calling drone controller.
This is drone control. Go ahead.
Are you ready to take control of drone?
Here goes.
All stations. Time is running. X-minus 25 seconds. DOVAP reports ready. Telemetry is ready. Flight safety is ready. Drone is ready. This is Nike Hercules Project Command. Time is running at X-minus 20 seconds. Mark. 19, 18, 17, 16, 15, 14, 13. Telemetry is down. Interference reported.
Range control to Nike Hercules. Telemetry is out. Over.
This is Project Command, holding at X-minus 10 seconds. We can hold 3 minutes before canceling the test. Out.
Range control calling frequency monitoring.
This is frequency monitoring. Direction finders are seeking source of interference. Out. Frequency monitoring to range control. Telemetry interference has been silenced.
All stations. This is Nike Hercules Project Command. At my mark, time will be X-minus 10 seconds. Mark. 9, 8, 7, 6, 5, 4, 3, 2, 1. Fire! Missiles away. All stations. This concludes the test. Thanks to all for your cooperation.
That was a fair sample of the service provided by the Integrated Range Mission, a service so unique that no previous experience has existed as a guide for its development. In fact, much of the book on how to set up and operate a missile range has been, and continues to be, written here. Today, the White Sands Missile Range is not only the hemisphere's largest and best instrumented land range, but also accommodates the heaviest test schedule. These tests are scheduled by all three services. Close to 3,000 major missions are forecast for the coming year.
IRM and its supporting organizations have their work cut out for a long time to come in providing optical instrumentation, electronic instrumentation, instrumentation research and development, central timing, range signal services, air support, missile test scheduling, processing and reduction of missile test data, and the recovery of missiles after firing. All essential tools on the frontier of missile technology.